Hello everyone, in this new video. In this video I'm going to talk about harmonic motion. So this is a simulation I made in order to understand this interesting phenomena. Now, let's stop. You can see that the values that I calculated using the differentials that are at the top of the screen agree pretty well with the values that are calculated by using the values using the formulas at the bottom of the screen. You can see velocity has an inverted sign, but it's just a tiny bug that will be fixed. So you can see that it is very interesting how the fastest the displacement changes, the faster the velocity changes. So now you can see the space is going to change really fast, the x space I mean. So the x velocity is also going to get big. Okay, are you ready? That was false. The x space changed slowly and the velocity was therefore slow. Now it is going to change fast. Are you ready? Go. Now it changed fast and the velocity was therefore big. Now let's look at the velocity. Okay. Now the velocity is going to remain pretty much constant. So the acceleration is going to be little. Look. We had a little change in velocity, so the acceleration remained little. Now we're going to have a faster change in velocity, so the acceleration will become bigger. Are you ready? Done. You have seen that the velocity was changing faster. Now let's look at an interesting phenomena, that is we're getting to see some deviation between the differential calculation and the formula calculation. That is because the errors are starting to add up, to stack up one over the other, and in sometimes the derivation calculation will be pretty much gibberish, and the only thing that will be correct and will be completely out of sync with this harmonic motion. So this is very interesting. In case you're wondering, in order to pause this simulation, you can just tap a key and keep the key pressed, and it's going to stop the simulation. Now, circular motion, you can see, velocity and acceleration, they're constant. But they are constant as the sum of the x part and the y part, a Pythagorean theorem. So 1 squared plus the other squared and all under the square root. All the two change continuously, but the Pythagorean theorem remains 20. It is the same thing that happens for the radius, but for the radius I have not written it because it is very obvious. It is just basic geometry. Instead, for velocity and acceleration it is a bit more interesting, so I wanted to write this down. So you can see, I will show you the code very briefly. So okay, let me show you the code. This is just some constant that are used to define the code. Now the really interesting part is right here, where you can see how the values are defined. So you see the velocity is the delta x out of the time step, and the acceleration is the delta velocity over the time step. The same is done for the y values. So you can see here is a sign error that we were seeing before, and here we can now fix the error that we had with the velocity that was of the wrong sign, the velocity of harmonic motion. So let me fix it in real time. Okay, so you can understand this code took some time to write, and I'm very proud of it. Because apart from all the numbers and the calculations that are also very interesting, and also it is interesting to see how the error increases over time, it is just very, very mesmerizing to watch. I mean, it is a contemporary work of art in my opinion. And yes, the formulas are just, the formulas are just the ones you know from high school, so they're very, very easy. Okay, there you sine and cosine and radius velocity. Okay, I will not comment on them, they're very, very easy. So the code is pretty easy. It is pretty long, but pretty easy. And what else to underline? Or I want to underline again this kind of very interesting sum, Pythagorean sum that always gives a constant value both for velocity and acceleration. Here you can see a bit of rounding error, and the fact that because the harmonic motion is a projection, you can see that the x value, the x components of s, v, and a, displacement, velocity, and acceleration of the circular motion, are the same as those of the harmonic motion. Okay, while the y component is like goes to waste. It is like, it would be translated to an harmonic motion with the diameter perpendicular to this diameter here. So I will add in the description both this file, both the code, the source code, the two applications to run this, one in Linux, one in Windows. And thank you very much. End of the video. Thank you for watching.